All right. So like I said, the first couple of days should be a little bit of review. If it's not, or you don't remember, that's okay. But we do need to get this stuff going before we get into anything too complicated. So first thing we're going to start off with is electronic structure. Oh boy, my computer is lagging pretty bad. Let's see if I can shut some of this stuff down here. I'll just give it a second. All right, so how do we describe the electronic structure of an atom? What are some things you know about the electrons of an atom? Anything? What do you know? They're in shells. Great. What else? They have interactions. In separate atoms, they're going to interact to bond and also repel each other. They have a negative charge. Yep. So we got shells, negative charge. What else? What's inside the shells? What do we call the things inside the shells? Yes. What do we call the place where the electron is likely to be found? Yeah, like those things. What are those called? Orbitals, yes, thanks. So we got orbitals, which are inside the shells, and we call them SPD. Remember all that stuff? Remember the quantum numbers, N and L and ML? So the good news is, we're not going to use those numbers anymore. I mean, not like forever, but like in this class we're not going to use them. But we are going to, it is going to be important to think about those electron configurations. So organic chemistry is primarily based on carbon atoms. So let's look at carbon first. How would we describe the electronic structure of carbon? Or what's the, we'll start here. How many electrons does carbon have? Total electrons. 6. Everybody got 6, right? From the periodic table. A neutral carbon atom is going to have 6 electrons. Okay, and how can we describe the orbitals that those electrons are in? Is what? 2 and then 4. So we're going to have 2 electrons in the first shell, the first n level, and then 4 in the second. Right? Absolutely right. So what do we call those 4 electrons that are out in the second one? Valence electrons. Good. Is it starting to come back a little bit? Remember some of these words being said by someone in the past? Yeah, so we've got those 6 electrons. We can say there are 2 core electrons and 4 valence. All right. And then we can further talk about the specific electron configuration of those 6 electrons. Anybody want to give that a shot? What's the electron configuration of a carbon atom? 1s2, that's a good start. Yep. 1s2, 2s2. Who's got the last bit? 2p2. Yep. All right, so that's all our 6 electrons. We've got 2 electrons in the 1s, 2 in the 2s, and 2 in the 2p. So the valence electrons are these, right? All right. Are those electrons all in separate orbitals, or are they in the same orbital? Or how can we be a little bit more specific about where those valence electrons are? They're the outermost orbitals, that's correct. So let's look at like the 2s orbitals. We said 2s2. Are those 2 electrons in the same orbital, or are they in different 2s orbitals? different, same. Kind of going back and forth here. They're in the same orbital. And how do we know that? How could we know that? How many s orbitals are in each shell? Do you remember? Just one. Yeah, just one. There's one s orbital in each shell. If you remember back to Gen Chem, the reason for that, or the explanation for that, had to do with those quantum numbers. That s is the L equals 0, and then it only has one possibility for ML, which is 0. But in this class, all you need to know, all you need to remember, is there's one s orbital in each shell. How many p orbitals are in each shell? Close. I heard somebody say 4, which is close. You get 6 electrons in the p's. How many orbitals are there? 3, yeah, right, 3. You get 2 electrons per orbital. So 3 p orbitals and 1 s orbital. And the great news is that in organic chemistry, in this class at least, we're not even going to mess with that whole middle of the periodic table. So do you remember those other orbitals, D's and F's? I mean, they're very nice. We like them. So as long as we are good with understanding the s and the p orbitals and the structures in there, that's a great start for what we need. Because we're going to be dealing with atoms like carbon, nitrogen, oxygen, hydrogen the most. And those are, because they're positioned in the periodic table, those are not going to be things that have expanded octets or d orbitals or any of that sort of thing. All right, so let's be a little bit clearer here that there are 3 p orbitals They're called the px, the py, and the pz because they point in those 3 different directions. So they're all perpendicular to each other, x, y, z. And each one can have up to 2 electrons. So when we say those 2p orbitals from carbon's valence, are they in the same p orbital, or are they in different p orbitals? Do we put the 2 in the same one first and then fill up the other ones, or do we fill them separately and then pair them up? So separately and then pair them up. Is that what you're going to say too? Shaking your head, yeah. Yeah. Anybody know why? So earlier somebody said electrons repel each other, right? That's why. When 2 electrons are in the same orbital, there's some repulsion there. So it's always a little bit better energetically for those electrons to be in separate orbitals, so they don't get in each other's way as much. So those 2 p orbitals in the carbon are actually going to be in separate orbitals, not paired up. And then that means there's going to be one more p orbital that has no electrons at all in it. All right. Let's look at another atom here. Let's look at hydrogen. How many electrons does hydrogen have? Just 1? And where is that electron? In the 1s, right? So its configuration is just 1s1. And then we'll look at one more. Another important atom for organic chemistry is oxygen. And how many electrons there? 8 electrons. And that configuration? Close. So we're going to start with 1s2. So we got 2 in the 1s, and then 2 in the 2s, and then 4 in the 2p. So that first shell here is our core electrons. And that's the valence there. So 6 electrons in the valence. Why do we make that distinction? What's important about valence electrons? We know they're the outermost electrons, but why do we care? Why make that distinction? Why use that special word? Yeah, they can be lost or gained. What else? They can determine polarity, so they can be used in those bonds and then moved around accordingly. So yeah, those are the electrons that do stuff. The core electrons are held so tightly by the attraction to the nucleus that they don't do any chemistry. They don't interact with other atoms. They don't get lost. They don't gain things. So that's why we care about the valence electrons, because the number of valence electrons will dictate what that atom actually does chemically, how it behaves. So that also means that atoms with similar, atoms with similar valence electron counts are going to have some similar chemistry. And in organic chemistry, we use that idea a lot. We use that idea a lot. So like oxygen and sulfur are in the same group or same family. They both have 6 valence electrons. And so a lot of the structures that we draw, we can draw the same types of structures for oxygen and for sulfur because of that. Same thing with the halogens, fluorine, chlorine, bromine, and iodine. Those are all going to do chemically similar things because they're all in the same family and they all have the same number of valence electrons. Okay, so now that we have a sense of electrons and what's going on in each atom, how do we talk about the connection of the atoms? So in general chemistry, we focused a lot on ionic compounds and ions, plus and minus, and all that. Organic chemistry, we care more about the covalent compounds because we're dealing with that right side of the periodic table. So how do atoms connect covalently? What happens there? They're sharing electrons. What does that mean? Yeah, I like that. Yeah, that's a good explanation. So it really is just a proximity effect. So the atoms are close enough together that the electron can exist in both orbitals or both valence shells at the same time. And that's our model of bonding. If you remember from general chemistry, we call that valence bond theory, or the idea that atoms have their own orbitals and then they come together and the orbitals mix. Now, there's a more powerful theory that you may or may not have done and have gone through in Gen Chem called molecular orbital theory that doesn't quite work that way. But for at least a while in this class, we're going to stick to that idea of valence bond theory. So we have our atomic orbitals, the atoms come together, and those orbitals kind of mix, and then the electron can be in both atoms or around both atoms at the same time. So how do we decide how many bonds a given atom is going to make? Like, let's try it. Let's try an example. Cl2, so chlorine, elemental chlorine. How can we draw a Lewis structure for Cl2? What do we do first?
Cl, dots around it. There's 7 valence electrons in Cl. Every side has 2 except one has 1.
Yeah, so that's one way to do it, is to draw the valence electrons on each atom and then look for where they can complete each other's valences. So for chlorine, how many valence electrons does each chlorine have? 7. So we could draw 7 valence electrons, 7 valence electrons, and then we could notice, oh, this one's kind of missing one, and this one's kind of missing one. So if those kind of came together and shared, then we could make a compound that looks like this. And then when we do our counting to kind of make sure everything works, we would say, well, this chlorine has 8 electrons. And this chlorine has 8 electrons. So everything's good. Yeah? Like, okay? What's another way to express those shared electrons in the middle besides the 2 dots? Yeah, we could use a line to represent that. So that line is also going to represent 2 shared electrons. And that means the same thing. Okay, so that's what we would call a Lewis structure. And in this class, that actually works most of the time. If you remember for general chemistry, you'd get to a point where you're drawing Lewis structures where this doesn't really work anymore, because the electrons have to be distributed more over the atom, so you have to like count up all the valence electrons from the atom and then redistribute them and make sure everything has an octet. You kind of remember doing that? We'll do a little bit of that too, just for practice. But organic chemistry, one of the features of organic chemistry is things are generally pretty well behaved. There's not as many exceptions with these types of things because of the atoms that we're working with. And so that way of drawing Lewis structures, which you used for inorganic molecules, is really maybe a little bit overkill for the organic molecules. But let's try some and take a look. All right, so here are some organic molecules that we're going to try to draw some Lewis structures of. I'm going to list a few, and then I'm going to ask you to just try to draw some Lewis structures of those molecules. Sound good? All right. All right, so here are 3 carbon-based molecules. Okay. And pulling from the recesses of your brain all the stuff you know about Lewis structures from before. Obviously, this is a bit of a jump from just Cl2. But let's see what you got. I'm not going to collect this or anything. Let's see if you can draw some Lewis structures for these. Take a couple minutes. And we'll look at them together. have some structures drawn. Doesn't matter how confident you are about them. If you could show them to some people around you and also look at their structures. My guess is they're not going to be identical. But if they're not identical, or if they're close, talk about that for a couple minutes. What's different about them? What's okay? What's not okay? If you can see legitimate things that you think are like mistakes or errors or things that don't work, if you feel comfortable, you can point those out. If not, you don't have to. But let's just take a look at each other's structures and see what they look like. How'd they look? The middle one was not good? What wasn't good about it? It was confusing? Okay. Didn't know how to do it? Okay. We had about 10 minutes left, so while you're thinking about it together, see if you can revise your structures or get some ideas. Does anybody feel like they want to draw one on the board up here? Yeah? Go for it. Thank you. Yeah, wherever there's markers and stuff. Anybody want to draw the second one?
Draw the third one?
Yeah, go for it. That's the advantage of volunteering, is you get to pick. I won't make anybody do the second one if they don't want to. Oh, you'll do that second one? Great, thank you. All right, what do you think about these? So good? No, not so good? Decent? Yeah, I think these all look great. So nice job. A couple of things to highlight here. I'll copy them just so we have them on the notes here too. So I'm going to draw them in a little bit different way, not because these are wrong, but because on Wednesday we're going to talk about geometry, bond angles, that kind of stuff, which becomes really important in this class when we start looking at these three-dimensional structures. So Lewis structures don't have geometry, or we don't care about the actual shape of the thing. All we care about is how they're connected. So we usually draw Lewis structures in this way that you all did, with basically 90-degree angles all around, because that makes it really nice and easy to see how everything is connected. That's totally fine. But when we start thinking about these as actual things floating around and how this one's going to bump into this one, and that's a lot of what we're going to do in this class, we're going to care a little bit more about the geometry, about what this looks like in 3 dimensions. So this first one, each carbon is going to have a trigonal planar geometry, so 120 degree bond angles. So it's going to look something like that. Again, I don't mean this as a criticism here, because these are all absolutely correct Lewis structures. I didn't tell you to draw it with the angles or anything. This one, same deal. Trigonal planar carbon. And then bent oxygens. I was also really happy to see the lone pairs, the non-bonded electrons on here. That's going to be really important in this class too. Those electrons are often what do the reacting. So we take the electrons from this molecule, we show that they attack this other molecule, and that's how they form this connection. So it's going to be important to account for all of those in our structures. And then finally, CH4 methane, which is actually tetrahedral. And we're going to, this semester, make a much bigger deal about that tetrahedral shape. And that dash and wedge, the wedge meaning that it's coming out at you, and the dash meaning that it's going back. If there's some different stuff connected here, that ends up being a whole thing. And it actually matters which thing is on which spot. So we're going to play around with that a bit as well. All right. So one other thing to learn from these structures. These are what we would call organic structures. Middle one's kind of back and forth, but organic structures. They're based on carbon. They follow the rules. Notice that carbon has 4 bonds in all of these. Hydrogen has 1 bond. Oxygen has 2 bonds. That's going to mostly be the case. General chemistry focused a lot on things like expanded octets and that sort of thing. We're not going to do that here because carbon doesn't do that. So organic chemistry is going to be a lot more predictable in this way with these types of structures. So on Wednesday, we're going to continue some of this review, and we're going to get a little bit more into how we draw these organic structures and what happens when these things get bigger and bigger. So I would like you to do a couple things for Wednesday. So first, please get ready for lab, meaning dress appropriately. Grab a notebook if you can. If you can't get a notebook by Wednesday, it's fine. But please print out the instructions. Remember that you have 500 pages of printing with your enrollment. So if you don't have a printer at home, you can go. I don't think it's 500 pages actually. It's like it's a lot. 200 pages, something like that. Is it 500 pages? $50. Okay, yeah. So you can go print out at the computer labs if you don't have a reliable printer at home. All of the lab instructions are on Blackboard right now. So if you know that it's going to be a problem to print like each week, you can just go print them all out, put them in a binder or something if you want. They're all there. You can get all your safety sheets done this afternoon for like all the labs if you want, because it's all there. You just got to look up the safety stuff. But please bring all that stuff in on Wednesday. Again, it's the first week. I'm not going to give people zeros if it's not done by Wednesday, but just to get in that habit of having stuff done before you come in, it's a good thing to do. So bring in your notebook and do all the preparation that we talked about. For class, I'd like you to review a few concepts from your previous chemistry class. You can use our book to do it because it's all in here. It's just all part of chapter 1. But if you have stuff from before that you really liked, if you want to pull that out and use it, that's fine too. But just a few things that we're going to definitely work on. So Lewis structures, as we just started. Geometry and hybridization. So remember like SP, SP2, SP3, that kind of stuff. Bond angles, all that. We're going to review that a little bit on Wednesday too. Polarity and electronegativity. think that's it. Yeah. And that's kind of stuff that I would consider review from a previous class. We're going to go through it on Wednesday, but the more you can kind of bring yourself back up from before, the better. Another little warning in terms of prerequisites. If you took Chem 110 or Chem 121, you did all of this stuff. If you took Chem 100 as your prerequisite, chemistry for the health sciences, you may not have done all this stuff. So if this seems like totally new, like you have no idea what's going on, please come talk to me after class. I can give you some other resources, kind of help you catch up. This class, not to scare you or anything, but this class is often really difficult for people who have only done Chem 100 as a prerequisite as opposed to Chem 110 or Chem 121. But if we start working early and we get caught up, I think it'll be okay. Any other questions before we go off? Okay, so I'll be in my office today from now until 1:45. So if you have any questions, come see me. Grab some more coffee on the way out if you want, and I'll see you on Wednesday. It was great to meet you all.